Swayam Prabha. Digital India. Educated India.
Welcome back. So far whatever the relationship, average variable cost, marginal cost, average total cost, all those relationship whatever we have established and how the diagram look like and all, right. So all those are basically in the short run, because look at here, some fixed cost was there, okay. So it is definitely a short run, okay. In the long run what will happen, the same producer, if you can remember, we told that long run all the factors are variable, there is no fixed factor, right. So, and we defined the long run in that way. Short run, that time span, and depending on what kind of production activity you are involved with, okay, where at short run is at least one factor is fixed, like the factory size, like this workshop size, stitching machine example we have demonstrated, right. And long run, even that workshop size is not fixed, right, that we told, maybe say 1 year is the long run in this particular case, maybe steel production, maybe 3 years is the long run, that we have discussed, right. So as you can understand, long run there is no fixed factor, as a result there is no fixed cost. So long run, whatever variable cost, that is the total cost only, because total fixed cost is 0, okay. So as a result, okay, so suppose this is the average cost curve, okay, and this is the marginal cost curve in the long run, and in the long run whatever SC, that is AVC also I can tell, because there is no variable fixed cost separately, whatever total cost, whatever total variable cost, that is the total cost, okay, and there is no fixed cost, because long run all the factors of productions are variable, okay. So this is the thing. So one clarification, okay, when we draw the short run curve, say suppose this is average cost curve, okay, this is average variable cost curve, they are coming closer and closer as output is increasing, output you are measuring this side, okay, and this kind of marginal cost curve you are getting, MC is the marginal cost curve. So all are U shaped and MC is cutting AVC at its lowest point from below, it is also cutting average total cost curve at its lowest point from below, okay, that we have done. So can you foresee that where this average cost curve will hit in the vertical axis? Because we can tell that average cost curve in the short run, this is the short run case and this is the long run case, right. Short run average cost curve should not touch the vertical axis in finite distance, okay, or alternatively we can tell that average cost curve can touch the vertical axis in the infinite distance. Why? Because short run a curve will cut or touch the vertical axis means what? You are essentially looking at when y value equals to 0, because you are measuring y in the horizontal axis, right. So output quantity is 0, that time what is your average total cost, right. So when output is 0, that time what is your total cost? Total cost in the short run, this is the short run case. So total cost is basically the total fixed cost, which is some amount of finite cost, maybe factory size, what is the rent, right. So your average, this was total cost, right. Total cost is the total fixed cost only, because there is no variable cost when y equals to 0. So your average total cost, okay, or sometimes which we called as average cost only, right. Average total cost is basically total fixed cost by y. So when y equals to 0, it is some finite total fixed cost by 0, that is why we can tell it is infinitely large, or average cost curve will never touch the vertical axis in the short run case. But is it true for long run case also? No, because in the long run case your total cost, okay, is basically total variable cost and there is no fixed cost. So average cost or average total cost, whatever way we can write, average total cost, it is basically total variable cost by output. Now when your output is 0, that time your total variable cost is also 0. It is variable. No, when you are producing output, you are not hiring any factor of production, right, because all the factors of production are variable. So, when your output is 0, that time your total variable cost is also 0. So, it is basically it is a limiting case when as a limit y tends to 0, that time you are reaching average total cost is basically 0 by 0. Okay. So, if you apply L'Hopital rule, okay, you will see that average total cost curve will hit somewhere in the vertical axis, okay, and marginal cost curve will start from the same point. Exactly the kind of relationship we had here for average variable cost and marginal cost curves in the short run. Exactly same sort of relationship will be there for the long run diagram, the average cost and marginal cost curves, okay, because here average cost and average variable cost are same in the long run. Okay. This is one thing. Okay. So, long run marginal cost curve and long run average cost curve, this is the relationships. On a totality, at the end we will tell that the kind of relationship that the marginal cost curve will cut the lowest point of the average cost curve and average variable cost curve from the below, okay, that relationship hold good here as well. But since it is long run, there is no separate average variable cost curve is there other than average cost curve, okay. And in other words, we can tell in the long run what is average variable cost curve, that is the average total cost curve. So, this kinds of only two diagram, one MC curve will be there and one average cost curve will be there, okay, and the relationship MC must cut that AC curve at its lowest point from below, okay, and they should start from the same point on the vertical axis, because when y equals to 0, the short run it is average total cost is infinitely large, because it is something finite by 0, but here in the long run it is 0 by 0. So, you have to apply L'Hopital rule. In fact, that L'Hopital rule we are applying here as well, okay, in this particular case short run, how that AVC and MC are starting from same point, we are applying L'Hopital rule. Exactly L'Hopital rule if you apply here, you will get that in the long run average cost curve will have a finite vertical intercept, okay. So, this is the thing, short run and long run three kinds of diagram how they look like, okay. Now, we will introduce three concepts regarding that, all of them are long run concept only. So, this is called returns to scale, returns to scale, okay. Let me first introduce by change in scale of operation what we are referring. Suppose I am a producer, right, I am using two inputs, say two input x1 and x2, okay. Suppose x1 is 5 units and x2 is say 9 units, and when I am using these two inputs, my output I am getting is say 15 units, something, some quantity, okay, 15 units, right. Now, if I change that x1 equals to 6 and x2 equals to 10, okay, and some output I am getting as a result, say maybe 17 units output I am getting, okay. So, this is, look at here, you are increasing both of your inputs, as a result you are getting some increment in your output. So, this is kind of long run kind of situation. Why? This is a situation what we are talking about, where both the inputs you can change. So, there is no fixed factor, both the factors are variable, right, it is a long run. But is it a returns to kind of, or is it a change in scale? No, but by change in scale we refer that entire input vector should be changed proportionately, okay. In other words, so suppose x1 is 5, x2 is 9, if you make x1 is say x1 is 10 and x2 is 18, then it is called change in scale of operation, means you are doubling the entire input vector, okay. Let me repeat, change in scale is a long run concept, where none of the inputs what you are hiring is a fixed input, okay, all are variable inputs. And when you are expanding or shortening your entire input vector proportionately, okay. Suppose I am making x1 equals to say 2.5 and x2 equals to 4.5, that is also change in scale, because you are making entire input vector half times, okay. In this case you are making the entire input vector double, okay. If you make say x1 equals to 5 into 1/3 and x2 equals to 9 into 1/3, that is also called change in scale. Scale of operation means you have to proportionately change the entire input vector, may be expanded, may be shortened, okay, shortened, okay. So, when you are changing that way, or when you are changing your scale of operation, how your output is changing, on that relationship we can define three concepts of returns to scale. One is called increasing returns to scale, another is called constant returns to scale, another is called diminishing returns to scale. So, by the very name increasing, constant and decreasing, you can easily understand increasing returns to scale, returns to scale is basically when the rate at which you are expanding your scale of operation or expanding your entire input vector, output is changing much more faster rate, okay. Output is expanding much more faster rate, then we will call it as returns to increasing returns to scale. How? Okay, suppose initially your x1 equals to 5 units you are using, x2 you are using say 9 units, okay, and output you are producing say 15 units, okay. When you are making x1 equals to 7.5, okay, x2 is basically 13.5. So, what you are doing? You are changing your scale of operation and you are making your entire input vector 1.5 times. Look at here, 5 its 1.5 times is basically 7.5, x2 was 9, its 1.5 times is basically 9 plus 4.5, so 13.5. And if your output is becoming 15's 1.5 times is what? 15 and 7.5, 22.5. If your output you are getting is greater than something, output, this was 15, right, output is greater than 22.5, then we will call that it is increasing returns to scale is operating there. So, the rate at which you are expanding your input vector, output is expanding much more faster rate. In this example, your entire input vector is becoming 1.5 times, your output is becoming more than 1.5 times, okay. So, that is why I wrote the new output is greater than 22.5, okay. Suppose old output is y1, new output is say y2, okay. This is alternatively, what is the decreasing returns to scale or diminishing returns to scale? Diminishing returns to scale, just the opposite. When you are expanding your input vector at what rate, okay, your output is not expanding at that rate, rather it is falling lower rate, it is expanding, output is expanding, but output is expanding at a lower rate, relatively lower rate. So, in this particular case, if diminishing returns is applicable, then your output should be y2 should be less than 22.5, okay. So, suppose when increasing returns to scale was operating, that time you are getting output y2 we are say 25 units, okay. But if it is a diminishing returns to scale applicable there, perhaps y2 will be say maybe 20 units, like that, okay. So, diminishing returns to scale is basically your input vector, let me repeat, the rate at which you are expanding your input vector, output is expanding, but output is expanding at a lower rate. Okay. And constant returns to scale, I think you definitely got an impression now that constant return to scale, by constant return to scale what we are referring, definitely the rate at which you are expanding your input vector, your output is expanding exactly the same rate, right. So, when you this case, if constant return to scale is applicable, that time your output should be exactly 22.5 units. Okay. Then the rate at which your input is expanded, input vector, not one input is expanding and another input is kept held constant, then so it will be only short run, right, because one input is held constant, right. First, as I told, returns to scale is a long run concept when you are expanding your entire input vector proportionally. So, since you are changing the entire input vector, so none of the component of that vector is remaining fixed for sure. So, returns to scale component concept is definitely a long run concept, okay. And that long run concept, when this is the thing, that time constant return to scale is applicable. The rate at which you are expanding, say you are doubling your entire input vector, your output also become double, then it called constant return to scale. Now, if that increasing returns to scale is applicable or is operating in your production activity, it is called economies of scale. Economies of scale. Economies of scale means the rate at which, say suppose if you double your entire input vector, your cost will be also double, because by default the factor markets from where you are hiring these factors of production, right, we did not tell anything whether it is competitive market or those are monopoly kind of nature, or we did not tell anything. So, by default those markets are competitive in nature. So, since those markets are competitive in nature, price is fixed. Competitive markets, one phenomena is price will be fixed, okay, that we will discuss in the next chapter in fact. Okay. So, the same price as many as you can hire. So, when you are doubling your entire input vector, right, so you are incurring the double amount of cost what you are incurring earlier, okay. But when increasing return to scale applicable, so that your cost is becoming double, but output is becoming more than double. So, as a result, average total cost, if you calculate, because average total cost is total cost by output, so it will definitely fall, no, because your total cost become double, output becomes more than double. So, as a result, say earlier your total cost was say 100 rupees and your output was becoming say 15 units. Now, your total cost becomes double, say 200 rupees, okay, and your output becomes more than double, say suppose 32. So, in this case your average cost was 100 by 15, but in this case your average cost becomes 200 by 32. So, definitely this is lower than this, right. 100 by 15 is exactly equals to 200 by 30. Since the denominator is more, it will be falling, right. So, as a result, if you have a long run average cost curve, okay, so this segment is basically increasing returns to scale is applicable, and we are measuring output here, and suppose here average cost, I am telling LAC, long run average cost, okay. So, we will get an U-shaped long run average cost curve. So, this segment of the long run average cost curve we will get when increasing returns to scale is applicable. This segment we will get when diminishing returns to scale is applicable in your production, and local CRS, because only one point where this slope is 0. Okay. So, we tell that local CRS. Okay. Sometimes you can have a average long run average cost curve, this kind of thing, which has a flat region which is horizontal. You are measuring output here and long run average cost in the vertical axis. So, this segment is increasing returns to scale is applicable or is operating there. This segment diminishing returns to scale is operating there, and this segment constant return to scale is operating there. When constant return to scale is applicable only one point, it is called local constant return to scale, sometimes it is called CRS, this is called DRS, diminishing returns to scale, and this is called IRS, increasing returns to scale. So, at this point it is called local CRS, only a small point where it is only CRS is applicable. Okay. So, as you understand that when when increasing returns to scale is applicable, that region we call economies of scale. Economies of scale means as you are expanding your input vector or as you are increasing your scale of operation, your production is becoming more and more economized. More and more economized means per unit of output you are incurring less and less cost. That is why it is called economies of scale. And this segment where the diminishing returns to scale is applicable, that segment sometimes called diseconomies of scale. Diseconomies of scale means the as you are expanding your output, per unit of output you are increasing more and more cost. Okay. That is called diseconomies of scale. Okay. So, a typical long run average cost curve, a typical long run average cost curve look like this. Output we are measuring in here and average total cost or average cost long run we are measuring here. So, a typical this kind of average cost curve we will get, okay, which will have this kind of flat segment. This is for constant return to scale, and that region neither economies of scale is there nor diseconomies of scale is there. This segment increasing returns to scale is applicable, and as a result we can tell that is the region of production where we are or that producer is experiencing or enjoying some economies of scale. More and more production, per unit of output less and less cost, okay, average cost. Okay. Per unit of output we are telling, so average cost. So, we can tell average cost we can interpret in this way, per unit of output less and less cost he is incurring. This is the diminishing returns to scale is area, okay, and there it is diseconomies of scale. Diseconomies of scale means what? As you are going that side or as you are increasing your output, okay, output production, your cost per unit of output is becoming larger and larger. Okay. So, this is the typical long run average cost curve. So, we have learned that what is the relationship between average cost, average variable cost and marginal cost in the short run, and average cost and marginal cost in the long run. Okay. But the question is why we are doing all those cost curves? Look, we are doing because these cost curves are very important for a producer or profit maximizer producer, any producer, no, any entrepreneur, okay, what he is doing, he or she is doing. He is engaged into some production activity, hiring certain factors of production, employing them into that production activity. Through that process he is able to generate some output, product or service, some output. That output he will sell in the market, he will get some sales revenue, okay, and that sales revenue, okay, whatever he is getting, from that he will pay that whatever factors of production he hired, their remuneration, okay, that lands he will pay rent, capital he will pay interest, okay, labor he will pay wage, and after those payments whatever will be there, that he will appropriate, that is called profit. So, definitely if I am the entrepreneur, okay, profit is my payment and I am controlling entire production activity, how much factors to hire, that I am deciding. So, definitely I will decide all those things keeping the objective in my mind, that so that I can maximize my profit. Okay. So, my profit or whatever my income at the end, that is called profit, right, my remuneration, that I will try to maximize. So, maximization of profit, that is the sole objective of any entrepreneur, any producer, that is the sole objective, right. So, in doing that what you will do, let me just clarify one thing quickly. Say my total profit is what? My profit usually denoted by this pi notation, but you can use your own own notation, okay, pi. That is basically revenue minus cost. This is the total sales revenue, what I am getting by selling my product or selling my service, whatever I am producing, that in the market, whatever total income I will get, that is called total revenue. And this is C means total cost, okay, by hiring those factors of production, whatever cost I am incurring to pay them, okay, that is total cost. So, this is my profit, total revenue minus total cost. Total revenue must be whatever price I am going to set for my product in the market, right. I am producing rice, right. So, at what price I will sell that sometimes I can decide, sometimes maybe market force automatically determine that. But whatever it is, that into the amount of output what I am producing, that will be my total revenue, and my total cost, that will be depending on some quantity, because look at all the cost curves, right. We have seen that cost is a function of output, that depending on how much cost, how much output I am producing, depending on that how much cost I am incurring, right. So, I can write total cost is a function of output quantity, okay, output we are denoting by y, right. So, total revenue is basically price into y, output, minus total cost as a function of output. So, this revenue, since here p into y, I can tell this revenue, total revenue, it also is a function of output, this y, minus total cost is a function of output. So, basically I will try to maximize my profit being an entrepreneur by selectively choosing the output quantity. So, I am the entrepreneur, my target is to choose that much of output so that I can get the maximum profit, okay. So, to do that what we can do, what? So, del pi del y, maximization condition, first order condition is what? Del pi del y must be equals to 0, and second order condition del 2y del y square, that must be less than 0. That is the first order and second order condition, necessary and sufficient condition for maximization of function. So, if we apply that here, it will be what? So, definitely del total revenue as a function of y by del y minus del TC as a function of y del y, that must be equals to 0 as the first order condition. So, this is we know as called marginal cost, okay, and this let us define, this is called marginal revenue. So, what is marginal revenue? Marginal revenue is basically the change in total revenue due to change in output, okay, output quantity. So, the way we have defined that total marginal cost, taking the partial derivative of total cost with respect to output, exactly the same way we can tell the marginal revenue is basically taking the partial derivative of total revenue with respect to output, okay, that is the marginal revenue, okay. Let me repeat again the definition of marginal revenue: change in total revenue due to change in output quantity. So, first order profit maximizing first order condition is MR minus MC must be equals to 0. So, MR equals to MC. So, this is the first order necessary condition to maximize my profit being an entrepreneur. Now, using this cost structure, right, in different markets we will discuss, next lecture onwards we will discuss, next lecture we will discuss competitive market. So, this producer whose cost structure is given in this by this TC kind of thing, this producer if he face a competitive kind of product market, output whatever he is producing, where he is going to sell that product, that market nature is competitive, what will be his optimum output decision or profit maximizing output decision, that we will discuss in that. So, basically in the diagram if we have this kind of marginal cost curve, I have to see where is the marginal revenue curve, and suppose this point MR equals to MC, that point MR equals to MC. So, we can tell that because this is the marginal cost curve and this is the marginal revenue curve, suppose. So, marginal cost curve is this U shape, means definitely we are measuring output in the horizontal axis, and marginal cost, marginal revenue, both we are measuring vertical axis. So, definitely since this is the first order condition to maximize my profit, I can tell either this point or that point my profit will be maximized. So, I will choose either this much of output or that much of output, But out of these two alternative, which exactly I will choose, that we will discuss exclusively or quite elaborately in the next lecture. So, this is why this alternative cost curves are required, because now onwards when we will discuss that optimum output choice of a producer, optimum in the sense that profit maximizing output quantity choice, right, we will use only a diagram. Where is the marginal cost curve, where is the marginal revenue curve, and where will be the equilibrium. Okay. So, that is why all these different cost curves are required, very important. So, that we have introduced here. Let us stop today, and in the next lecture we will start competitive market or a producer's optimum output quantity decision in a, if he is going to operate or going to sell his product whatever he is producing to sell in a competitive market. Okay. Let us stop here.